Welcome to the Deep Dive, your shortcut to being well informed. Today, we're plunging into a really fascinating corner of artificial intelligence. We're looking at how we're teaching powerful neural networks to see and understand the world, not just on flat screens, but on curved surfaces, specifically spheres. Our mission for this deep dive is to unpack why the usual AI methods kind of stumble when they face spherical images, and then how a groundbreaking approach called Spherical CNNs completely redefines how AI sees the world and what incredible real-world problems they're already starting to solve. Our source material for this deep dive is the foundational 2017 paper Spherical CNNs by Cohen, Geiger, Kohler, and Welling.
Yeah, what's genuinely exciting about this research is how it takes the incredible power of regular convolutional neural networks, or CNNs, the ones behind things like face recognition and self-driving cars, and basically bends them to work in entirely new curved dimensions. It's tackling a fundamental blind spot AI had when looking at certain kinds of data.
Okay, let's try and unpack this challenge then. We know CNNs are absolute superstars at analyzing ordinary 2D planar images, like, the ones from your phone camera. But the paper immediately flags a huge problem when you move to spherical images. Why can't we just take a 360-degree spherical view, flatten it out like a map, and then just use a standard CNN? It sounds simple, right?
You'd think so, but the core issue is just severe distortion. Imagine trying to teach a computer to recognize a cat on one of those flat world maps. If the cat moves near the poles, it gets stretched all out of shape.
Like Greenland looking enormous.
Right, and that's essentially what happens when you project a spherical image onto a flat surface. These distortions, they make the fundamental principle of traditional CNNs, which is translational weight sharing, utterly ineffective. A pattern recognized in one spot might be completely unrecognizable just a few degrees away on the projected map because its appearance just changes due to the projection itself.
So on a flat image, if something moves, it's just a simple slide of translation, left, right, up, down. But on a sphere, a move is fundamentally a 3D rotation. That completely changes how you need to think about pattern recognition, doesn't it? Because that classic CNN filter, the little window that just slides across, that just won't work the same way.
It really creates a foundational mismatch. What feels like a simple slide on a flat image becomes this complex three-dimensional rotation on a sphere.
Yeah.
And this is where traditional CNNs just hit a wall because their core assumption of simple translational filters breaks down. For a plane, the space of moves is just, well, two-dimensional translations.
Yeah.
Simple. But for a sphere, that space is the three-dimensional world of 3D rotations, known technically as SO3.
Yes.
Don't worry too much about the jargon. Just think of it as the collection of all possible ways you can rotate something in 3D space. It's a much more complex space of moves than just sliding left or right. And this distinction means that if you perform a spherical correlation, the sphere equivalent of convolution, the output, isn't a signal on the sphere itself, which we call S2. Instead, the output is a signal on SO3, on this space of rotations. It's a subtle but profoundly important difference from planar CNNs.
Okay, so these researchers basically had to go back to the drawing board and completely rethink how a CNN operates for a spherical world. What are the groundbreaking building blocks they designed for these spherical CNNs?
Well, they started by proposing a new definition for spherical cross-correlation. In a normal planar CNN, you compute the output by sliding a filter across the input and taking an inner product, sort of measuring the match at each spot. For spherical correlation, they replace those filter translations with rotations. So the value of the output feature map at a particular rotation R is calculated as an inner product between the input feature map and a filter that's been rotated by R.
Okay, that makes intuitive sense. Instead of sliding, you're rotating and matching. But I imagine implementing that must come with some massive headaches in practice. What were the biggest practical challenges they ran into?
You're absolutely right. There were two major hurdles they identified. The first is what they call the grid problem. On a flat image, pixels form a nice, regular, square grid. It's easy to define shifting a filter by, say, 1 pixel. But on a sphere, well, there's no perfectly symmetrical grid of points that allows for simple, discrete rotations like 1 pixel over. Think about lines of longitude converging at the poles.
Ah, right. The spacing changes.
It does. This means defining a filter rotation isn't straightforward. You constantly need interpolation, essentially guessing the values between points. The second, and perhaps even bigger challenge, was computational efficiency. Because SO3, this space of rotations, is three-dimensional, a direct, naive implementation of this SO3 correlation would be incredibly expensive. We're talking O in 6 complexity. Yeah. To put that into perspective, if n was the size of even a moderately sized image, A direct calculation might literally take centuries. It's completely unfeasible for anything real world.
Okay, so that computational hurdle is huge. We'll definitely need to come back to how they solved that. But first, beyond just a single layer, how did they ensure that as information passes through multiple layers, the network continues to understand patterns regardless of their orientation? That's where this idea of equivariance comes in, isn't it?
Yes, equivariance is really the magic word here. It's a crucial property shared by all types of convolution and correlation, planar or spherical. And it's what makes CNNs so powerful for pattern recognition in the first place. A layer is called equivariant if doing something to the input like rotating it and then processing it for the layer gives you the exact same result as processing the original input first and then applying that same rotation to the output.
Okay, so rotate then process equals process then rotate.
That's the idea. This property is what ensures the weight-sharing scheme, using the same filter across different locations or rotations, remains effective across multiple layers of a spherical CNN. It allows the network to detect patterns, maybe a specific constellation in the sky, or a particular molecular structure, regardless of its rotation on the sphere. It means the network sees a cat as a cat, whether it's right side up or completely upside down on that sphere.
So they've got this new, elegant mathematical definition of correlation for spheres and this crucial equivariance property. But with that ON6 computational problem looming, how on earth did they make this actually work efficiently? That's usually where brilliant theoretical ideas hit a practical wall.
Right, and this is where the paper introduces some really powerful techniques from a field called non-commutative harmonic analysis. It sounds complicated, but the core idea is analogous to something we use all the time in regular CNNs. Just as the fast Fourier Transform, the FFT, revolutionized how we efficiently perform convolutions in planar images.
By turning convolution into multiplication in the frequency domain, right?
Exactly. It turns out there's an analogous transform for functions on the sphere and the rotation group SO3. This is called the generalized Fourier Transform, or GFT, and thankfully there are corresponding fast algorithms, the GFFT. Think of it this way. Just like the standard FFT lets us quickly analyze the frequencies or patterns in a flat image signal and perform operations more efficiently. The GFT does something similar, but for these more complex spherical and rotational patterns.
Okay, so it's a way to break down these spherical signals into fundamental components.
That's a good way to put it. Conceptually, the GFT projects a function onto a set of special orthogonal basis functions. For the sphere, S2, these basis functions are spherical harmonics. You might have encountered them in physics or chemistry. They're like the natural vibration patterns of a sphere. For the rotation group SO3, they use something called Wigner D-functions.
Wigner D-functions,
Yeah.
okay.
Think of these as the specific mathematical notes or frequencies that describe rotations in 3D space, much like how a musical chord can be broken down into individual notes. By using these specialized basis functions, the spherical correlation satisfies a kind of Fourier theorem. This theorem allows the computationally expensive correlation to be computed much more efficiently using these fast GFFT algorithms.
So just like an FFT in a regular CNN converts that complex convolution into simple element-wise multiplication in the frequency domain, this GFFT does something similar for spherical data, making the whole thing actually tractable.
That's the perfect analogy, yes. For these SO3 correlations, the Fourier theorem states that the GFT of the correlation is essentially the matrix multiplication of the GFTs of the input signal and the filter. The actual implementation of the SO3 FFT is clever. It involved performing a standard 2D translational FFT over specific angles that define the rotation, called Euler angles, and then combining that with some pre-computed values related to those Wigner functions. The S2 FFT for the sphere itself is similar, using a 1D FFT and other functions called Legendre functions. This transformation into the frequency domain and the use of these fast algorithms is the absolute key to overcoming that ON6 barrier and making this approach practical, not just a theoretical curiosity.
That's an incredible computational leap. The theoretical framework sounds incredibly robust and elegant now. But what does all this complex math and clever computation mean for real-world problems? The paper showcases several experiments. What did they find about the numerical stability of their approach? You mentioned approximation errors earlier.
Right, stability is crucial, especially for deep networks where errors can compound. They rigorously evaluated what they call the equivariance error, basically, how much their practical, discretized implementation deviates from perfect rotation and variance. They found that while this approximation error does grow slightly if you increase the resolution or stack more layers, it remained remarkably manageable. even when they added a standard RILU activation function after each correlation layer, which can sometimes mess with these properties. The error, although a bit higher, stayed flat. It didn't explode.
Okay, so it didn't run away, suggesting the core method is sound.
Exactly. It indicated the error wasn't fundamentally coming from the network layers themselves piling up, but more from the initial step of representing the feature map on the sphere grid, which is only perfectly exact for mathematically smooth signals, so-called band-limited functions. This ability is really important and strongly supports the practical accuracy and reliability of their algorithm, even when building very deep spherical CNNs.
That's a critical detail for deep learning applications. What about a head-to-head comparison with traditional CNNs? They tested this using a special spherical MNIST dataset, right? What did that reveal about the core advantage here?
Yes, the spherical MNIST experiment was a truly eye-opening result. It's a powerful demonstration of the spherical CNN's strength. They took the familiar MNIST handwritten digits numbers 0 through 9 and projected them onto a sphere. They created two versions. One where the digits were always in a fixed orientation, and another where they added extra random rotations.
Okay, so one easy version, one hard version with rotations.
Right. A standard planar CNN, trained on flattened projections, performed well on the non-rotated data, achieving around 98% accuracy, pretty good, but its accuracy absolutely plummeted down to just 23% when the digits were randomly rotated.
Wow, from 98 down to 23.
And even worse, if you trained the planar CNN only on the non-rotated digits and then tested it on rotated ones, the accuracy dropped to 11%. It basically couldn't generalize to different orientations. The spherical CNN, however, it maintained high accuracy consistently across all scenarios, staying around 95% to 96%, whether the digits were rotated or not.
That's a massive difference. It's not just a slight improvement. It's like it fundamentally understands rotation.
It really is. It empirically shows the utility of spherical CNNs for rotation-invariant learning. It allows the AI to see and understand objects on a sphere from any angle, something previously just impossible with standard methods on projected data.
So it's not just incrementally better, it's fundamentally enabling new capabilities for spherical data. They also apply this to some pretty different domains, 3D shape recognition and even molecular energy prediction.
Yeah.
Tell us about the 3D shape recognition on the SHREC-17 task.
Right, so for 3D shape classification, like identifying different types of furniture or vehicles or animals from their 3D models, they used a fairly straightforward method called ray casting. They essentially projected the 3D mesh onto an enclosing sphere from the inside, capturing 6 different channels of information about the shape's surface properties at each point.
So turning the 3D object into a multi-channel spherical image.
Precisely. Then they fed this into their spherical CNN architecture. This typically started with an S2 convolution block operating directly on the sphere, followed by several SO3 convolution blocks, processing information across rotations. And the results. It performed very competitively. While it wasn't always the absolute #1 method in the SHREC-17 competition, which had highly specialized approaches, it was consistently among the top 3.
That's impressive, especially for a more general method.
It is. It provides strong empirical support for the effectiveness of spherical CNNs without needing loads of a complex, handcrafted feature engineering. The network seemed to learn the relevant features naturally from the spherical representation.
And finally, molecular energy regression. That sounds complex, predicting chemical properties like atomization energies just from the molecule's 3D geometry. How did spherical CNNs tackle that?
For this, they used the QM7 dataset, which is a collection of small organic molecules with known properties. They needed a way to represent the molecule as a spherical signal. They generalized a common chemical representation called the Coulomb matrix. For each atom in the molecule, they essentially defined a sphere around it. Then, on that sphere, they created potential functions representing the influence of different types of neighboring atoms, carbon, hydrogen, etc. This resulted in a multi-channel spherical signal centered on each atom.
Okay, so each atom gets its own spherical view of its neighbors.
That's the idea. They then use a deep resonance-style S2 CNN, a robust type of deep neural network architecture designed for spheres sharing weights among all the atoms. They also used a technique to ensure the final prediction didn't depend on the order in which the atoms were listed, which is called permutation invariance. Their spherical CNN achieved a root mean squared error, or RMSE, of 8.47 on predicting atomization energy.
How does that compare?
It outperformed all the standard kernel-based machine learning approaches tested, and also a standard neural network, an MLP, trained on sorted Coulomb matrices, which was mentioned in related work. Only one other method, an MLP trained on randomly permuted Coulomb matrices, showed slightly better performance, but the paper notes that specific method doesn't scale well to larger, more complex molecules.
So another strong result in a very different, highly scientific domain.
Yes, it further validates the model's effectiveness and its potential for scientific discovery. So what this deep dive really demonstrates, I think, is that spherical CNNs provide this theoretically sound and empirically validated solution for all class of problems where traditional CNNs just, well, they struggle or fail. The research presented here clearly defines these S2 and SO3 cross-correlations. It introduces that incredibly efficient, generalized FFT-based algorithm to make it all practical, and it provides really compelling evidence of its utility across diverse, rotation-invariant learning problems like 3D shape recognition and molecular energy prediction.
It truly highlights how extending the core principles of deep learning, things like convolution and weight sharing, to different geometric spaces isn't just some academic exercise. It literally opens up entirely new possibilities for AI. And the paper itself, it points to several exciting future directions for this groundbreaking technology, doesn't it?
Indeed it does. This work is often seen as an important first step towards generalizing even further. One major direction is moving beyond just rotations, SO3, to the full rototranslation group, SE3. That would handle objects that are both rotating and moving in 3D space, which could be incredibly significant for intrinsically volumetric tasks, like analyzing medical scans or understanding how complex objects interact in 3D.
So analyzing the full 3D volume, not just the surface projection.
Right. Another generalization mentioned is the development of what are called steerable CNNs for the sphere. These would allow the analysis of vector fields on the sphere, things like global wind directions on a planet, or stress patterns on a surface, where not just the magnitude but also the direction at each point matters.
And looking even further ahead, the paper itself hints at perhaps the most transformative possibilities for this technology. The most exciting future application identified seems to be an omnidirectional vision, 360-degree cameras for things like advanced drones, mobile robots navigating complex spaces, and of course, autonomous cars. Imagine a self-driving car that can truly see in 360 degrees without the distortions and blind spots that plague current systems that try to stitch flat images together.
There's 10 tool, yeah.
So this research provides a really powerful new tool for analyzing data that inherently exists on curved surfaces. It moves us closer to a future where AI can interpret the world spherical or otherwise with much greater accuracy and efficiency. What stands out to you as the most impactful aspect of spherical CNNs as we look towards the future? We encourage you, the listener, to consider how these fundamental principles might apply to other areas where data isn't perfectly flat.